Okay, so in the last two lectures, we looked at some basic overview of the course and also the project theme, the financial cryptography, and we started the first section of the course, which is classical cryptography. And in the classical cryptography, so I'm going to discuss a couple of ciphers, which were earlier, they were pretty common. And we will also see how some of them can be broken very easily, okay? Because now we understand them in a much better manner. And some of them are still okay to use, basically. And so these ciphers normally uses the alphabet A to Z, right? Because English is a popular language, of course. And now from A to Z, so there are 26. We convert them into 26 uh, numbers, right? 0 to 25. So essentially they map into finite ring integer modulo 26, right? So that's why we started looking at integer modulo n in general for any n, right? Or integer modulo m. And we know that this is a ring. It is not a field from algebraic structure, from mathematical point of view. And it is a field if and only if m is a prime number. So Zp is a field. That means Z2 is a field, Z3 is a field, Z6, Z5 is a field, Z6 is not a field, Z4 is not a field, Z7 is a field, and so on, right? So the question is, because why do we need a structure of field on the algebraic structure or the alphabet? Because most of it's very easy to do operations on the packet. So normally the packets in the internet or anywhere you see, they are part of this field with 256 number of elements. So ASCII values, So 8 bits. So 8 bits, one packet, right? So basically, so we need to have a better understanding of the system. That's why we should study finite field. Okay. So field with finite number of elements. So last lecture I just gave you some basic idea about how to construct a field with 4 number of elements. I'm going to now talk about it in more details. And then I will also talk about field with 8 number of elements, right? And in general, how you can construct a field with certain number of elements. It's a very, very important. And I think every computer scientist should know about this. It's a very, very basic, whenever we are operating with packets, so whenever you're doing cryptography, whenever you're doing fault tolerance or providing, error correction, you're designing codec, you require finite field. So very, very useful topic. So if you really want to understand, say, how machine learning you can work on encrypted data, you should understand what is field. It's a very, very important thing, right? So I'm going to cover probably today. I should be able to cover all the basics. I'm not going into too many details, but at least the idea should be clear to you, right? How these things works, how you can think about it. Okay, so we are talking about classical cryptography, and I think I already gave you. So this integer modulo m is a ring, right? In general, and it's a field with m is a prime number. So we talked about. So the question was how to construct a field with 4 number of elements, and I gave you this analogy. As you can see here, from reals to complex. So this is very, you know what are complex numbers, right? So definition is a plus ib. That's a common thing. Now, but where this I came from? Why should we need I, right? So the thing is that we have real numbers, which are fields. So basically, in terms of infinite fields, there are 3: field of rational numbers, field of real numbers, and field of complex numbers, right? So from real numbers, how do we construct field of rational numbers? And the technique is the same whether you do it for infinite fields or whether you do it for finite fields. Okay. So technique is that look at a irreducible polynomial over the ground field, right? So for example, over reals, look for a polynomial which has no root. Okay. And then attach a root. So suppose I is a root. So for example, x square plus 1 is equal to 0. It has no root on reals, right? So we can attach a root. We call the solution as I, Because then suppose I square plus 1 is equal to 0. That means I is equal to square root of minus 1. Now square root of minus 1 you cannot plot on the real line, right? So we need to extend the domain, right? Now when we need to extend the domain, so I am attaching on the reals this I, and the mechanism is that now this new field, each member will be a plus ib, such that I square plus 1 is equal to 0. So I is the root of this equation, which is irreducible, means you cannot find any root in the ground field. Got it? So this is the basic idea. So from using x square plus 1 is equal to 0, I can construct field of complex numbers. Same idea, now we are saying that now I want to construct field with 4 number of elements. So what should I do? I take a ground field. So now the ground field is Z2, which is binary field 0, 1. You know, we saw that last time Z2 is a field, right? Every non-zero element has an inverse because 1 into 1 is equal to 1, right? And all other with respect to addition, everything is satisfied, right? So now, if you take a polynomial of degree 2, so what are the most general form of a polynomial of degree 2? It's ax square plus bx plus c, right, is equal to 0, where a is not equal to 0. So normally we know that if a, b, c are reals or complex, how to solve them, right? You can apply Sridharacharya formula and then you can find the roots, right? Sometime it is real, sometime it is complex, and so on and so forth. Now, the best thing is here. So one thing is that, of course, we don't have that kind of formula here, but what we can do here, since A, B, C are finite things, A can take only one choice, and B and C can take only two choices, because A should be non-zero, so A should be 1. So the equation reduces to x square plus bx plus c is equal to 0. And now there are 4 equations possible, right? 2 choices for B, 2 choices for C, 0, 1, 0, 1. So I can write down all the 4 equations and I check by plugging the values of 0 and 1 in each of these 4 polynomials, and which one has no root in the ground field, Z2, right? So I'm just checking x square plus x equal to 0. Will it be a reducible polynomial? No, because 0 and 1 both are root here. X square plus 1 is equal to 0 is also not working because x equal to 1 is a solution. X square is equal to 0 is also not working because x equal to 0 is a solution. So the only polynomial left is x square plus x plus 1 is equal to 0. Because if we plug in x equal to 0, we will get 0 plus 1, which is non-zero. And if we plug in x equal to 1, 1 plus 1 plus 1 is 1, modulo 2. 1 plus 1 plus 1 is 3, modulo 2 it is 1, right? So that means this is the right kind of polynomial. So I can take this polynomial to construct field with 4 number of elements. So now what I should do, suppose there we have assumed I, now I change the symbol alpha, okay, because you should not confuse with same I. So I'm calling this symbol as alpha. Suppose alpha is the root of this equation, that means alpha square plus alpha plus 1 is equal to 0, right? And then we can construct field with 4 number of elements, like a plus ib kind. So a plus alpha b such that a and b are in Z2 and alpha square plus alpha plus 1 is equal to 0 in the exactly same manner. Got it? Everything analogy we have taken. Now we see how many elements are there. Obviously, now a plus alpha b, if you know that a has 2 choices, 0 and 1, and b has 2 choices, 0 and 1, that means there are 4 elements possible, right? So one will be 0 plus alpha times 0. Another one will be 1 plus alpha times 0. Another one will be 0 plus alpha times 1. Another will be 1 plus alpha times 1. So that means 0, 1 alpha and 1 plus alpha. 4 elements are possible, right? Now the question is it forming a field? How do we check? So what I suggest, again we can make the tables, addition table and multiplication table. And normally with addition everything is working fine, but problem happens with respect to multiplication table. So we need to make sure that every non-zero element has an inverse, right? Now one thing we need to keep in mind that here alpha is root of the equation alpha square plus alpha plus 1 is equal to 0, right? Now once we are dealing with this kind of equation, I need to keep certain things in mind, that alpha square alpha plus 1 is equal to 0 means alpha square is equal to minus alpha plus 1. Now minus alpha plus 1 is same thing alpha plus 1. Why? Because the ground is in Z2, right? The coefficients are in Z2 only, right? For this polynomial. So when we are adding, right? So when we are taking this on the other side, so basically minus 1 is same thing as plus 1. Okay, because the coefficients are in Z2 anyway of these polynomials, right? So that means, so now we keeping these things in mind, and also note that alpha cube I can compute what is the value. Alpha cube turns out to be 1. So let us see that calculation. So alpha cube is equal to alpha into alpha square, which is alpha times alpha plus 1, because what, why alpha square is equal to alpha plus 1? Alpha square is equal to minus times alpha plus 1, same thing as alpha plus 1, right? So we substituted here. So you simplify, it turns out to be alpha square plus alpha. Now alpha square plus alpha is same thing as 1, because alpha square plus 1 is equal to 0. So that means alpha square plus alpha is equal to minus 1. And minus 1 is same thing as plus 1, right? So we are having alpha cube is equal to 1, right? Another important thing, anything twice is 0. So 2 times alpha is 0. 2 times alpha square is 0, right? Because modulo 2, everything will be 0. The coefficients are in Z2. We need to remember always, whenever we are working with these polynomials, coefficients are in Z2 only. So we need to follow those operations, right? Now let us make a table. So I'm writing, so basically now the elements 0, 1, 1 plus alpha, alpha can also be written as 0, 1, alpha square and alpha. So there are two representations of the field with 4 number of elements. One representation is known as polynomial representation. In the polynomial representation, each element of the field is a polynomial. So one is, so one way is 0, 1, 1 plus alpha and alpha. These are 4 polynomials, right? Another way is power representation of alpha. Everything is a power of alpha. For example, if because a 1 plus alpha can be written as alpha square, so all elements can be written as 0, 1, alpha, alpha square. Now it's much more convenient to do the calculations with the powers of alpha. Okay, so then I can just write down 0, 1, alpha, alpha square, 0, 1, alpha, alpha square, and do all the additions. I can say that 0 plus 1 is 1, 1 plus alpha is alpha square, because 1 plus alpha is equal to minus alpha square is same thing as alpha square, and we can do all the calculations. So table with respect to addition is very good. Looks like everything is fine. Now when we go to the multiplication table, I can write down 0, 1 alpha square, 0, 1 alpha square. Keeping those operations in mind, I can make the table. Now you note that, so when I have to check whether every non-zero element has an inverse. So wherever there is a multiplicative identity in the table, I will look at the corresponding paired elements. So for example here, if you look at this one, so this shows that 1 into 1 is equal to 1. That means 1 is self-invertive, right? 1 into 1 is equal to 1. Now we look at the second multiplicative identity, which is this. The corresponding pairs are alpha and alpha square. Because alpha and alpha square is equal to alpha cube and alpha cube is equal to 1. So that means alpha and alpha squares are inverse of each other. Right? Same thing with here, alpha square and alpha. So every element has an inverse. One is self-invertive, and alpha square are inverse of each other. So every non-zero element has an inverse. So actually it is a field. Right? Very, very important, beautiful concept, right? So a common confusion that happens when we say that construct a field with 4 number of elements, people normally think, okay, Z4 is a field because Z2 is a field, Z3 is a field, so they make a table for Z4, yeah, it is a field, without actually looking at that Z4 is not a field because 2 into 2 is equal to 0, right? 2 has no inverse in Z4, okay? So there is a difference. Both has 4 number of elements. And those who are expert in modern algebra, are there some people who have done a course on abstract algebra or modern algebra or algebraic structures? Yes. So you must be knowing how many groups are there of order 4? There are only 2 groups of order 4. These are the basic questions, So very common interview question also. How many groups are of order 4? How many groups are there of order 3, 5, 6? Beautiful. Okay. Anyway, so this is all about Z4. Now we go to the next one. So Z4 is done. So Z2 is done. Z3 is done. Z4 is not a field, but we have a field. Galois field with 4 number of elements. It's based on the name of Johannes Galois, right? He was a very famous mathematician. At a young age, he died actually. For the love of a woman, actually, he had a fighting. And before that, he wrote all these calculations and sent it to his friend. Anyway, so it's something nice thing what he has done. So now, what about 5 number of elements? We have Z5. 6 number of elements, Z6, is it a field? Why? Because 2 into 3 is equal to 0. And none of them is 0. So 2 and 3 are 0 divisors, right? So they will not have an inverse when you make the table. Okay? So Z6 is not a field. But can we construct a field with 6 number of elements? It's a T problem for you, right? See if you can construct field with 6 number of elements and tell me the difficulty when you try to. So one way of looking at this problem, if due to just mathematical curiosity, just try to make a table with 6 number of elements such that addition everything is satisfied and multiplication you can somehow take care. You will realize the problem that you cannot fill the table actually. Okay, so 6 is not possible. Okay, 7, we have integer modulo 7. 8, integer modulo 8 is a field? No. But is it possible to construct a field with 8 number of elements? Yes, because it is a power of 2. In fact, you will observe that when you do these calculations, whenever we are constructing a field with number of elements as a power of 2, it is very easy to construct. Okay. Okay, so that is one property that you can later on prove also, that whenever we are trying to construct field with q number of elements, it should be power of 2. Or more general, it should be power of a prime number. So field with q number of elements exists if and only if q is a prime power. Okay, that is a key thing. And why this is coming? Because you see, we want to construct Z4, we have constructed field with 4 number of elements. We can construct field with 8 number of elements. So, from Z2 or GF2, I can take a polynomial of degree 2, I will get field with 4 number of elements. If I take a polynomial of degree 3, I will get field with 8 number of elements, right? If I take a polynomial of degree 4, I will get field with 16 number of elements and so on. So power of 2 is easy to build. Just take a irreducible polynomial of that degree. If you want to construct field with 2 raised to power L or whatever, 2 raised to power S. Suppose you want to construct a field with 2 raised to power S element. So you should take a irreducible polynomial of degree S over the ground field to construct the field. Okay, which has no root in the ground field. So from Z2 you can build the tower. Z2 to ZF4, ZF4 to ZF8, ZF8 to ZF16, ZF32, and so on, right? And in between somewhere there will be field with 256 number of elements. 256 is power of 8, 2 to the power 8. So you need to take a degree 8 polynomial to do all the calculations, right? So let me show you now calculations for field with 8 number of elements. So you see it is already written with field with 6 number element is a t time problem. You can just see if you can make a field or not. You will realize that you cannot when you try to fill the table. Okay, so Zn is a field if and only if n is a prime number, fine. Z of 8. Now, if you want to construct a field with 8 number of elements, right? And this is Z 256 2 raised to power 8. So every element here is byte. One byte is 8 bits, right? So element of field with 256 element is each element is known as byte, 8 bits, right? It's a very common notation, basic building block of computers, right? So okay, so now how do we do it for field with 8 number of elements? Let us see that. By the way, just before closing, so there are 3 representations of the field elements. One is polynomial representation with 4 number of elements, 0, 1, alpha, alpha plus 1. Second one is power representation, 0, 1, alpha, alpha square. And the third one is bit representation. What do you mean by? These are the values of A and B in A plus alpha B. When both A and B are 0, 0, 0, right? Then 1, 0, then 0, 1, and 1, 1. All 4 elements you can write. So there is a bit representation, there is a power representation, and there is a polynomial representation. So each finite field has these 3 kind of representations. So these are useful when you do the calculations, write a computer programs, and so on. Which representation you should use, all those things. So basically, you can represent everything in the form of bits, and you define these tables for doing the operations, and you are done, right? For doing the calculations, okay? Okay, so now Okay, so now we try to construct field with 8 number of elements. The G of 8 is 2 cube point 2 raised to power 3. So I should look for a degree 3 polynomial. So I have written that ax cube plus bx square plus cx plus d is equal to 0. It's all high school mathematics, right? By the way, in high school, do you know how to solve a degree 3 polynomial formula? For degree 2, you have Shridharacharya formula. For degree 3, which formula? Unfortunately, it is not taught, right? But it's Cardan's cubic solution. It's a beautiful solution, right? You should look at it sometime. So you can give a formula for degree 2, you can give a formula for degree 3, you can give formula for degree 4. Question for you, why you cannot give formula for degree 5 onwards? Think about it. It's a very basic. All this mathematics, arises because of daily business, right? And you want to do business anyway. So you should know how to solve equations. If you know how to solve equations, you can do a lot of applications, right? So this is very important. Anyway, so now, again, A, B, C, D. There are 2 choices for each. So how many choices? A is, of course, having only 1 choice because A should be non-zero. So A is 1. So the equation is x cube plus bx square plus cx plus d. Now B, C, D has 2 choices each. So there will be how many? 8 equations. Got it? So now we can write down all these equations. I think I have written all these 8 equations. Now let us check which one is going to work. If I look at x cube plus 1 is equal to 0, is this a right equation to work? No, because x equal to 1 is a solution. 1 plus 1 is equal to 0, right? So we cannot do that. What about the other equation, x cube plus x is equal to 0? No, because x equal to 0 and x equal to 1 is a solution, right? Then we go to this equation, x cube plus x square plus x plus 1. X equal to 1 is a solution. We cannot do that. What about x cube plus x square is equal to 0? No, because 0 is solution, 1 is a solution. X cube plus x square plus x is equal to 0. No, because x equal to 0 is a solution. But then we arrive at 2 equations which are irreducible, which has no root in the ground field. One is x cube plus x plus 1 is equal to 0, and another one is x cube plus x square plus 1 is equal to 0. So if you plug in x equal to 0 and 1, in both of the cases, we have no solution. Now what? We wanted to have 1 equation so that we can build the field, but now there are 2 equations. What to do? Any idea? Why anyone? Yeah, who said anyone? That is correct answer, but why? Resulting field will be isomorphic. Good, that's a mathematical answer. Beautiful answer. So basically, when we say isomorphic, means their algebraic structure is exactly same. You can map one element to the other element by some map, right? So which is 1 to 1 and on to, right? So that is a possibility, right? So you can pick up any one. So, normally, I think here I will show you calculations using one of the polynomial as a T problem, because you need to drink tea in the evening, right? Or coffee, whatever. You take the other one, okay, and try to make these tables, and then find that map which maps one field with the other field, okay? So that you can really enjoy the beauty of mathematics, right? So let me show you one calculation. Okay, so field with 8 number of elements. I have taken the polynomial x cube plus x plus 1 is equal to 0, right? X cube plus x plus 1 is equal to 0. And then, so alpha is the root of that equation. That means alpha cube plus alpha plus 1 is equal to 0, right? And then just choose different values of a, b, c. You will get 8 elements as a power of alpha, right? You want to do some calculations here. For example, can you find polynomial representation for each? Polynomial representation for each. So normally, since it will satisfy power of alpha, I know, but otherwise, what you need to do, plug in the values of a, b, c, and then write down the polynomial into compact power of alpha, right? So this is an easy exercise for you to do actually, right? Keeping in mind that alpha cube plus alpha plus 1 is equal to 0. That means alpha cube is equal to alpha plus 1. By the way, which power of alpha will be 1 here? 7, because alpha is power 7 is equal to alpha into alpha is power 6, which is alpha times alpha cube whole square, no problem. But alpha cube is equal to alpha plus 1, because from that equation, so this is alpha plus 1 whole square. Now a plus b whole square is equal to a square plus b square modulo 2, because 2 times ab will be 0 anyway, right? So you are left with alpha square plus alpha. There is some problem here, right? This should be 1 here, right? Yeah. And so when you multiply, it's alpha cube plus alpha, right? This should be 1 here, right? And so alpha cube plus alpha from the equation is 1, right? So alpha is plus 7 is 1. So this is 7th root of unity over the finite field, not over the real or complex. Remember? So cube root of unity I told you. Similarly, this is 7th root of unity, but over finite field. It's not over the other field. So now I think you can make the tables easily. Should I leave it for you to complete the table at the t time? Right? And so remember, your job is to take another polynomial also, which is alpha cube plus alpha square plus 1 is equal to 0, and make the table here, and then map. And I think we have done this in discrete math course, right? If you have done a course with me, so I'm just recollecting all the facts. So what about field with 9 number of elements? So we are done with 2, 3, 4, 5, 6 is not possible, 7 is possible, 8 we have done. What about 9? So 9 is 3 square. So the ground field will be Z3, right? And the polynomial should be of degree 2 over Z3 to construct the field. 1 minute. Okay, so right. So here polynomial is A plus alpha B. So I think you can observe that in case of G of 8, we took A plus alpha B plus alpha square C, right? You can keep on taking the powers higher as you build the system, right? That is the key idea. So now here, again, you can look at degree 2 polynomial and do all these calculations. So it is an exercise for you. Very good. To construct a field with 9 number of elements. So you have to drink 4 or 5 cups of coffee or tea today to do these exercise and recollect. It's a pleasant weather, right? Sit in the cafeteria, take a cup of tea and do the calculations. And by the way, there is a famous mathematician who said that if you want to understand algebra, the beauty of mathematics, get a comfortable seat, take a cup of coffee, pen and paper. There is no need of Google, mobile or anything, right? Just do the calculations. Mental exercise, right? Okay. So in general, if you want to do construction of field with 2 raised power m elements, I take the polynomials like this, right? A0 plus A1 alpha plus A2 alpha square plus dot 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 AM minus 1 alpha raised power m minus 1, where each AI is in Z2, and we need to look for a polynomial f of x. So alpha is root of a polynomial f of x, which is of degree m and which is irreducible over Z2, which has no root over. So this is the whole philosophy, how to construct any field with power of 2, right? And if you want to construct field with p raised power m elements, the ground field should be ZP. Everything will remain the same, right? So I hope you understand the basic idea. And so basically this polynomial representation can also be written in terms of powers of alpha. 0, 1, alpha, alpha square up to alpha raised power 2 raised power m minus 2, right? So as an exercise, again, construct field with 16 number of elements. 16. So you need to take a degree 4 polynomial. So here you can take this equation, x raised power 4 plus x plus 1 is equal to 0, right? And you have already done this in discrete path class, fine. People who are from maths and computing background, I don't know whether they have done it. If they have not done it, they can do these calculations, right? Okay. So this is how the tower is Z2, ZF2 square, ZF2 cube, and ZF2 raised to power m. Any question about the finite field business? Now we can go to the next thing. Any question about this finite field business? Everything is clear? So you understood everything? If there is no question, again, I always say that there are two things. Either you understand everything or you don't understand everything, right? So I hope the good thing is there anyway. So this is the more general thing for P raised to power m, from ZP to GFP square, GFPQ, GFP raised to power m. Right. And I think if you ask your juniors, I have given them this beautiful problem in the quiz. Still, they are searching for the solutions, right? So it was that ax square plus bx plus c is equal to 0, where a is not equal to 0, and abc in say z6 or z4 or integer modulo 4 or integer modulo 3. How do you solve? Can you give a formula? They are still struggling. Maybe you can help them. And for that, you require another cup of tea or coffee. Anyway. Okay, so now I think we have about 15 minutes or so. So we can actually talk about the crypto system. So now you saw some basic mathematical preliminaries. Now the crypto system, as I said, initially I'm going to talk about classical crypto systems, and we are assuming that they are members of Z26, integer modulo 26, right? Because we can map the alphabet. So by the way, I asked you one day what is the size of Sanskrit alphabet or Hindi alphabet or Devanagari or whatever Indian language you take, any Indian language, and try to build crypto system there, beautiful. But of course, the idea will remain the same. But anyway, so we have normally crypto system is 5 tuple mathematically. T is finite set of possible plain text which is not encrypted. Okay, it's a plain text. It could be anything. So normally people assume initially integers or whatever, some alphabet, right? So plain text. C is the finite set of possible cipher text. Cipher text means encrypted data. Okay, encrypted data. Then K is a key space. Again, a finite set of possible keys. Okay, some keys to encrypt the data. Normally, we can say that okay, if there is a plain text, you apply a key, you get an encrypted text, right? That is the thing. You can take one key from the key space. Okay. And so the condition is for every k in key, so for every key in the key space, there is this encryption rule. You should have an encryption rule, EK, okay, which belongs to E, and a corresponding decryption rule, DK, such that EK maps plain text to the cipher text, and decryption rule maps cipher text to the plain text. If you can encrypt, you should also know how to decrypt. Otherwise, it will not work. And this condition is that EK of, so DK of EK of X is X for every X in P. इसमें क्या है, this is a common sense writing, right? But you can define and you can write for the sake of completeness. So this is a very basic crypto system definition. Now, if we take plain text to be xi, I can make a vector also. X is equal to x1, x2, xn, right? So then I can say that where yi is encryption of xi by this function ek, right? So we'll get a vector y. So basically, I can talk about data which is kind of a vector rather than an integer, right? I can, or some single thing, right? Single bit. We have a vector, we can do the same thing. If P is equal to C, if the plain text is same thing as cipher text, this may happen. In that case, this encryption is nothing but a permutation, right? It's a permutation essentially, right? Because this cipher text and plain text are the same. Okay, just encryption, just some permutation. Okay. So the first example is shift cipher, which you know from your discrete math class, right? Shift cipher, very popular cipher. what is shift cipher? So here, plain text space, ciphertext space, and key space is same alphabet, integer modulo 226, Z26, right? Okay. So now, we can have a key, some number between 0 to 25, right? Key could be anything, k, small k we are writing, anything between 0 to 25, right? So that means ek of, so in fact, encryption rule is ek of x is x plus k modulo 26. So we are just shifting by k, right? So x plus k modulo 26. Because we are taking modulo, we are actually rotating, right? We are shifting. Okay. And then dk of y is whatever you receive y minus k. Okay. So you get decrypted modulo 26, right? So this is the shift cipher. Very early days cipher. And I think you can clearly see that if you write down all alphabets A to Z in the form of this 0 to 25, all these elements, we can do this mapping easily, right? And then we take a English sentence and then we write down the encryption rule. So let us see that example here. We will meet at midnight. By the way, I am taking all these examples, everything from the Douglas Stinson book, so that you have something to read. These days, people do not read, right? They only search on Google. So that's why I do suggest, please do have something additional. I cannot put everything on the slides, right? So some things are there in the book. So get the book, and again, either in the evening or tea time, you can casually look at the book, right? So, okay, so that sentence is, we will meet at midnight. If I choose k is equal to 11, our key is 11, number 11. So then we will meet at midnight will correspond to 22, W is 22, E is 4, and so on. These numbers, k is 11, you add everything 11 and reduce it to modulo 11, sorry, modulo 26, you get this. You convert it back, you get something like this, right? So this is encrypted text. Plain text is, we will meet at midnight. Encrypted text is HPHTWW, I don't know, whatever way you read it, right? So the question is, how good is the crypto system? Now, one very basic thing, what is known as exhaustive key search, EKS. EKS is a very popular term given to these things. Can you exhaustively search the key? In this case, yes, right? Because what happens, we know that there are only 26 numbers, right? To 25 numbers, 0 to 25 total, right? So what you can do, of course, if you add 0, you will get the same thing. That's a separate thing. But what you do, take this, convert into the numbers, and keep on trying key one by one, right? And after certain trial, can you tell me how many trials you will get the answer? That's a probabilistic question. So you think about it at a tea time, right? So, okay, so that is something. But you will see that you can. So this is another exercise. You find the plain text. You will see that here it turns out that after trying different decryption keys, D0, D1, D2, D3, that means trying different numbers from 0 to 25, you will hit the, so you can write a small program also if you want, right, which will just search, and whenever it is matching, Cryptanalysis is a very, very fundamental thing, actually, Analyzing the crypto system, that it is secure, is a very, very fundamental thing. So we try to make crypto system where exhaustive key search is infeasible. Even if you write a very good computer program, it is going to take 10,000 years to actually get the key. So then you can sleep nicely after taking a tea. Anyway, so let us look at next is substitution cipher. So here again, so substitution cipher, plain text and ciphertext are integer modulo 26, same alphabet. And K is basically a kind of permutation we are applying. Okay, permutation of 26 symbols. Some permutation we are applying. So basically, permutation you know, right? कहाँ पढ़ा था? Permutation group is very beautiful thing. Symmetric group, SN, AN, all those things, right? Math is really beautiful. You can enjoy. Anyway, so if you have this permutation pi, so x you apply e pi, you get pi of x, right? Some permutation, and decryption is inverse permutation you apply, right? So let me see how to do this. For a random permutation pi, so for example, if you see here the small letters A, B, C, D, E, F, G is the actual symbols, and capital letters are encrypted ones. So basically after applying the permutation, so A goes to capital X, basically A goes to X, B goes to N, C goes to Y. We have written here capital so that you know that which one is encrypted, which one is plain. Okay, so A, B, C, D goes like this. So permutation, so A goes to X, right? B goes to N and so on. C goes to Y, D goes to A and so on, right? This is a permutation. Okay. So you can write down this mathematically also, right? Permutation like 1, 2, 3, 4, those n symbols or 26 symbols, and then which permutation is used. First is going to which? X. X, what is the number of X? 24 or something, I don't know. Yeah, you can calculate, right? So basically, you can just write down those numbers, right? 1, 2, 3, and then down at the bottom side, you write down the values, right? So which symbol goes to which position? So you are just writing the positions, right? So similarly, this is a decryption function. So basically, if there is a permutation, there is an inverse permutation also. So essentially, this is just a substitution. And substitution cipher has been studied a lot in the literature, right? A lot of people have done this earlier. Something, initially they did not realize that, whether you can break these systems or not, but they were using it. Now, again, see, now at each point, you have an exciting opportunity for competitive programmers to write a small computer program to break these crypto systems. So for example, this permutation one, can you break it? So this is the text. Can you break? Some permutation is used on the 26 symbols, right? So what you can do, write a small computer program. Now you see that how many choices are there? There are factorial 26 choices, right? So now factorial 26 choices, this is something, a number very large. There is an approximately, it's bigger than 4 times 10 raised to the power 6, a very large number. So exhaustive key search is infeasible. So this is a good system. So I think if you want to be a good cryptographer, you should have this habit of writing small programs, try to break the crypto system. So your first exercise, this time in your computer center, but I think you don't have a computer center here, right? So maybe in your library, sitting with AC, and try to write a small program to break the system. Can you break it? You will see that your program will say that, please forgive me. I cannot do that, right? So that feeling you should have, right? Basic thing. So that's all for today. So we'll see a couple of more beauties next time. Thank you.